It's my great pleasure to have with us today Marcus Dantus, a University Distinguished Professor and MSU Foundation Professor in the Departments of Chemistry and also Physics and Astronomy. He has pioneered the use of spectrally and temporally shaped ultrafast laser pulses. Marcus joined MSU in 1993 after receiving his doctorate from the California Institute of Technology in 1991, where he worked with Ahmed Zewail, the 1999 Nobel Prize winner in chemistry, on the development of femtosecond transition rate state spectroscopy, which is now known as femtochemistry. Now, we all know in laboratory sciences it is the graduate students who really do the bulk of the work. And so that Nobel Prize, some of that Nobel Prize credit should go to our colleague. A femtosecond is 10 to the minus 15 seconds. And thanks to this gentleman and his colleagues, we can now image chemical reactions on those timescales. So we can actually see what molecules are doing on a timescale of 10 to the minus 15 seconds. And furthermore, there are many, many applications of this technology, not just in pure science, but also in defense and other important areas. At MSU, Dantus has published more than 200 scholarly articles and has been issued 25 patents. He's a member of the National Academy of Inventors and a fellow of both the Optical Society of America and the American Physical Society. He regularly collaborates with different branches of the U.S. Department of Defense and has collaborations with other research groups at Harvard, UC Irvine, and Case Western Medical Clinics. Welcome, Marcus.
Thank you. Well, good morning. It's a pleasure for me to have this opportunity to tell you a little bit about the application of these lasers that for a long time they remained in the laboratories because they were so difficult to adjust. When you're talking about pulses that are a millionth of a billionth of a second, you can imagine that any vibration in any of the mirrors makes them not function properly. And I'm going to tell you today a little bit about the technology, very little, but primarily focus on the application of these lasers to biomedical imaging and diagnosis. So a few years ago, it was actually in 2001, that I started thinking, what are the practical applications for these lasers? And as I was thinking about that, I realized that the big problem of the lasers was that you needed graduate students working on the laser all the time, and therefore you couldn't take them out of the laboratory. And that's when we invented and developed this technology that's in this box, the MIPS technology, which automatically compresses these pulses. And then fast forward a few years later, we developed this fiber laser, so you can see the fiber glowing. So the laser is going through the fiber, and these lasers can be made very compact, and together with our technology become incredibly powerful, as I'm going to illustrate today with respect to biomedical imaging and diagnosis. So in particular, you need a little bit of focus to kind of focus the effort in the laboratory. So we figured skin cancer is the most commonly diagnosed cancer in the United States. Breast cancer is very important, especially the margins in surgery. 250,000 new cases are diagnosed per year in the United States. And then retinal diseases, which affect diabetic retinopathy affects about 4 million people, and macular degeneration affects about 8 million people in the US. So these are very big problems. And I'm going to tell you how these femtosecond lasers can be brought to the diagnosis and in some cases treatment. The first part I'm going to talk about is melanoma. So melanoma turns out to be a very small fraction of the skin cancers. However, the staggering number of melanoma is a person dies of melanoma every hour. This is how terrible it is. And the idea of this is, right now, we, often procrastinate a little bit before we call the doctor's office. Then when we call, dermatologists happen to be incredibly busy, and so it might be 2-3 months before they can see you. And then when they see you, they say, well, yeah, I don't like it. Let's schedule a biopsy. And that could be another month, and then you do the biopsy, and then, a week later, you're anxiously waiting for the result. And the result of the biopsy is going to be based on how do the cells look, right? So the pathologist is going to use morphology primarily. And like, well, it looks good or it doesn't look so good. And sometimes, if it doesn't look very good, they need to, again, establish margins. And so one of the bad calls to get is like, well, sorry, but you need to come back for a little bit more surgery. Well, that means we left something inside of you, and it's been growing ever since. So the idea is, wouldn't it be amazing to have a laser that I can scan the tissue and get more information. So yes, get the morphology, get information inside of the skin, in depth. But also if we can have more chemical information that would tell us, based on the morphology and the chemistry, we now know this is melanoma. It needs to come out right now. Don't go home. Don't schedule let's do it now. So that's the idea. And I'm going to show you some results. I presented some of our early results at a conference, and the director of the Beckman Laser Clinic at UC Irvine, who is kind of behind the idea of using the laser to look through the skin, he's like, wow, your results are really amazing, but for me to know, I need to know how they compare directly with my system. Is there any way that you can send your laser from MSU to our clinic and we can put them side by side? So because our technology is compact, we took the technology and it was taken to side by side, and I'm going to show you those results side by side. So the top results are with their laser that has been as optimized as possible for skin imaging. And what you're seeing is a cross-section of the skin. Now the key, there are two things to notice. The first is the purple and the green, that's chemical information. And in this case, the purple is melanin, the green is the collagen in the skin. And what we show is in the left-hand side, these are results from their laser, these are results from our laser. What we see is we still have the chemical information. The big deal is that if you see in the bottom screen, we see twice as deep in the tissue with our laser. And then I will tell you that our laser has half the energy of their laser. So that, and it's much less damaging to the tissue. So these are incredibly exciting results that point the way to the future of lasers for skin cancer diagnosis. And they are now tested at the place where this is happening. So this is very exciting. So let me just touch on the issue of breast cancer. Now, this laser will only, the femtosecond lasers that we have, will only penetrate, say, about 1 millimeter, which is not enough for deep tumors. However, during breast cancer, again, the key is to make sure that the entire tumor has come out and that we have clear margins. And so, therefore, what would happen is during the surgery, that's the ideal case, that the tumor is sliced and that the pathologist can declare that we have clear margins. Now, again, those calls are being made by morphology, and it would be good to have chemical information. Now, traditionally, chemical information has involved the injection of contrast mechanisms. And the problem with that is that, well, then it depends on the circulation of blood around the tumor. Did it have enough time for the stains to get to the right places? What I'm going to show you is stain-free imaging of a breast cancer tumor with femtosecond lasers. And the key here is that the femtosecond laser can get that chemical information. And I'm not going to explain. I'll spare you the details of exactly how that happens. So here what we have is, this is all the same slide. No dyes have been used. And we're able to look at the water content, the lipids, the vasculature, so we can see certain veins here, collagen, and biomarkers, so that the pathologist can get chemically information-rich that the pathologist can use for making a diagnosis. So this is, again, another very big development. This in collaboration with Professor Bopart at the University of Illinois Urbana-Champaign, and this is also a recent paper. And then finally, I'm going to be telling you about our recent work in retina. So the retina would be, if we think in terms of 21st century, would be the CCD of the eye. It's way in the back. That's where all the photoreceptors are. And because of macular degeneration and diabetic retinopathy, the retina begins to decay, and that leads to blindness. And it's very, very important that the doctors are able to see what's going on in your retina. But because your retina is way back there, it's very difficult, so they can only see the surface. And so what we need is something that will penetrate deep into the layers of the retina, and that, again, if we can have this chemical information reach, chemical information so that the doctor can make a good determination of what's going on, that's the key. So I'm going to show you here some of the new slides that we have of a retina. This is a mouse retina. And what we can see is the multiple layers. So if this would be like if we were looking at the eye inside like this. And so these are all the multiple layers. And what we're doing, so this is current work. We are now beginning to break down the different signals into their different colors and their different chemistries. And there is a very good distinction. So this is very, very exciting. You can see the level of detail. So we see subcellular resolution. With, this would be the rods and cones that allow us to see in color and black and white. So I have two concluding slides. The first one is that this work is going from fundamental laser development to the chemistry and then to the collaboration with engineers and medical clinics. And this is something very exciting happening both at MSU and outside of MSU. And finally, this research gives the opportunity to a very large number of students and postdocs. So this is not the current group. This is throughout my time at MSU, these are some of the students that have participated in this kind of research. So with this, I thank you for the opportunity to let you about.